Hello, my name is Dave Rolleman and welcome to RetroWired's 4-wire system. Today we are going to introduce two new systems that are currently not available in the automotive industry. These two systems will provide automotive manufacturers with huge savings and increased functionality at the same time. Automotive manufacturers for years have been looking at vehicle networking. Vehicle networking is where you have small computers, we will call them modules, talking to each other through the vehicle network to get a job done. For instance, one module that has a light switch tied to it will send a message on the network that the lights need to be turned on. Another module on the headlights will turn on the headlights upon receiving the message. Since all the modules in the car work together on a network, each can send a message for what function it needs to employ. Up to this point, vehicle networking has been cost prohibitive. The current vehicle networking systems on the market have proven to be too expensive to fully implement or just don't work properly. Automotive manufacturers have struggled with putting in new technology while maintaining the old wiring harness method. So what automotive manufacturers have done is put in CAN bus, but its use has been limited to a few controllers per vehicle. With today's current processing power of microcontrollers, RetroWire developed the Challenger operating systems. All the functionality CAN bus can provide, Challenger provides, but with more intelligent functionality. RetroWire does things a little differently. With CAN bus, the hardware filters out what messages to pass on to the controller. With RetroWire, this is done in the Challenger multitasking operating system. With Challenger, it does everything but handle device-specific operations. Second, the new Flex 485, the crystal-less communication system, with high reliability within a harsh electrical environment. With 2 years of on-road testing, this makes the new system ready for the automotive market. Challenger's multitasking operating system controls the handling of the messages. It handles all the analog to digital conversion. These are just some of the functions that are done in the background. So device-specific hardware does not need to handle this. So when we need to send a message, we format a message, then tell the operating system to send the message. The operating system then handles the sending of the message. Then Challenger on the receiving module will decode the messages and pass only messages for the device, ignoring all other messages that are not pertinent for this device. When we need information from the analog to digital converter, we only need to look at a register, as the conversion has already been done by Challenger in the background. The system works by sending messages. For instance, a light switch will send a message to turn on the headlights. The headlight controller will receive the message and turn on the headlights. The taillights will turn on the running lights. The dashboard will turn on the backlighting. As we can see, a single message can be picked up by multiple modules and handle them differently, with only one message sent. On the receiving side, some modules may process up to 15 different messages from other modules. When it comes to programming the device, we include Challenger plus our device-specific code. If we take the light switch, the specific code for this is only 10 lines. Because Challenger takes care of the rest of the functionality, this makes it easy to add modules to the system. Challenger's multitasking capability is capable of receiving messages, acquiring analog to digital conversion, all while running time-sensitive foreground tasks. For example, we can send new timing table to the ignition computer while the engine is running. We also have the ability to manually control the timing while driving down the highway. This just shows the ability of Challenger's multitasking capability. Another example is an LED-based dashboard that with a single controller handles communications, multiplexing of the LEDs, no multiplexing hardware, and a menu-driven 2x16 line VFD screen. This is done on an 8-bit controller running at 8 MIPS, million instructions per second. Challenger is not an operating system that will run Word or Excel because it's specifically designed for automotive use. The efficiency and small footprint allows that some devices have an EEPROM memory of only 2K. There's a saying, a picture is worth 1,000 words. In this case, boy, is it true. If we take a look at this wiring diagram, it fits on one page. Not since the Model T days could a wiring diagram fit on one page, while maintaining the current high levels of technology. The simplicity of the system of only 4 wires really shows itself here. With RetroWired, we use 4 wires for the entire car. These same 4 wires are interconnected to all the modules in the car. there are only two types of connectors in the entire car. First, the high power connector. This connector is used under hood or where more than 1 amp is required, and watertight connectors are required. For example, we have a drop connector to a wiper motor. This motor is not directly connected to the switch which controls it, as its previous connection had 6 wires, 4 connectors, and 18 feet of wire. Now we have 18 inches of wire and 1 connector for the wiper motor. The second connector is the same one on your telephone jack in your house. Modules that require less than 1 amp, not requiring water-type connections, use this connector. Traditionally, vehicles like police, fire, and ambulance use special wiring harnesses. They usually remove part of the existing wiring harness to install their own. Now with RetroWired, this would be a firmware change. So this means no wiring harnesses would need to be replaced for specialty vehicles. At most, you would add more drops for added functionalities of the vehicle. To add optional equipment is easy. For instance, to add a remote starting would require no additional wiring, as it would be only a matter of adding a module. To further enhance RetroWired's system, we created Maverick. Maverick connects to the vehicle via a USB port. This port converts the Flex 485 signals to USB. This Windows software has the ability to control, diagnose, and watch the system operate. Because the operating system on the modules operates in the background, we can communicate live from Maverick to any module without interfering with its operation. This screen shows what the switch settings currently are. It also shows fuel level, battery voltage, engine temperature, transmission temperature. Since the cost of LCD glass is getting cheaper, the graphics here could be ported to a new LCD screen dashboard. Currently, only high-end cars using LCD for navigation and some vehicle functionality. With this, the whole dashboard could be LCD. This page is for setting up timing values of the ignition computer. Watch live what is happening currently and to override settings all while the engine is running. This vehicle is equipped with an electronic GM 4L80E transmission. This transmission does not have the capability of shifting on its own, so a controller must do it. On the left hand side of the screen is the manual controlling of it. We have the ability to using this screen to manually control what the pump pressure is, what gear it is in, and whether the torque is going to be locked up. On the right hand side we have the shift points of the different gears and the set points. In the center we have live data coming back from the controller of the status of the transmission. This screen shows the data coming back from the wideband oxygen sensor. It shows how rich and how lean the mixture is. It also shows the current bias point, how much the heater is on, and so on. On the bottom of the override box, you can select a tab as to which module you wish to override. Once you have selected the tab of the module you wish to control, you can then select the function you wish it to perform. For instance, you can turn on the wipers. On the right hand side of the screen shows a list of running modules. You can also ask the system for an immediate update of all the modules on the system. This would tell us the modules that are communicating, and from the list we can look for the module we're interested in for whether it is running or not. This could be useful for diagnosing the system. This diagnostic tool is handheld and is great for testing the system. We can view electrical system status, watch what messages are being sent, or what modules are on the system. For instance, if there is a problem with wipers not functioning, we could test right up to that connection by placing the tool right where the wiper motor would be connected. First, we would detect whether everything is working up to the connector. First, do we have voltage? Is the communication okay? Then look down for the wiper settings. With this hand tool, we can walk around the vehicle plugging in to finding out up to the connector whether everything is okay. When CAN bus was developed in the early 80s, computing processing power was very limited. So at the time, CAN bus technology was a fantastic breakthrough. Today, however, the processing power has greatly increased, so this method is now out of date. Bosch has since developed a new technology called FlexRay, but again with this technology, costs are still high and still based on the old technology, just faster. The limitations that CAN bus FlexRay start with: licensing. A license fee must be paid for every node, and due to the low tolerance of CAN bus's data rate of 0.5% and FlexRay's 0.3%, makes these controllers not very fault tolerant. they also require crystal on every node. With Flex 485, this is not an issue, as we use the internal oscillator of the microcontroller and not worry about tight tolerances. The cost of the crystal and its capacitor is only 25 cents. If you multiply that by 10 nodes per vehicle minimum, and 72 vehicles produced, equals $180 million just in crystal cost. If we take the extra cost of CAN bus controllers of $2 per node times 72 million vehicles, that's $1.44 billion. These are just some of the examples of just how much extra CAN bus costs if you were to install it fully in every automobile produced. These costs are not incurred by RetroWired system, and FlexRay costs are just higher. It also requires special wiring. With CAN bus, it is highly recommended to use shielded twisted pair. This just increases the cost of the harness more. Now let's look at some of the savings that can be obtained using RetroWired's 4-wire system. Here are the current costs. Copper, $75. Manufacturing from copper to wire, $25. Connectors, $25. Manufacturing wiring harness, $22. Installation of wiring harness, $12. Engineering costs, unknown. Switches, $25. Current modules cost, $75. Total, $234, which translates into, with 72 million vehicles, $16.8 billion. Here are the costs to implement the RetroWired system. Modules cost, $45. Wiring harness, $12. Installation of wiring harness, $7. Total, $58. Now, 58 times 72 million vehicles equals $4.2 billion to implement RetroWired system. So if we look at the cost to implement the current wiring harness method versus the RetroWired method, we can see that $16.8 billion for $4.2 billion with a saving of $12.6 billion. So a manufacturer wouldn't implement this system with nearly instant return on investment. Since releasing our alpha release 2 years ago, the stability of the system has greatly improved. With a 50 to 70% dollar savings from the current system, this also reduces vehicle weight, it saves on manufacturing a wire and connectors, and less copper to be mined. With RetroWired, most electrical problems can be diagnosed in minutes as to what module or apparatus has failed. With new diagnostic tools, diagnosing problems with the system is easy now. With RetroWired's Challenger operating system, Flex 45, and just 4 wires, we can now move away from point-to-point wiring, with the average savings of over $176 per car and the intelligence level greatly increased. Thank you.